Alright, hello everyone. It's December 6th. So today's plan was first we're gonna handle whatever it is today we have to do, and after that we'll go back to the wiggle sort. I'm gonna go through the proof step by step, and trying to write the solution in on time and on extra space. It's complicated to do it that way. But it was a shame that I wasn't able to come up at least this solution. But anyway, we'll talk about this later. But for now, let's go for the question today. I got an easy one, so let's just get it done and move on. Minimum cost to move chips to the same position. Let's see. Okay. Have those before? Yeah, I have. Like last year. Okay. N chip's position of the ith chip is position I. Position of the ith chip is this. We need to move all the chips to the same position. In one step, we can change the position of the ith chip from position I to either +2 or -2 with cost 0, +1 -1 with cost 1. Return the minimum cost needed to move all the chips to the same position. So at position 1, 2, 3, the chip 1 is at position 1, chip 2 at position 2, and chip 3 at position 3. I have n chips. The ith chip is position. Okay, I got it. So first step, we're gonna move the chip at position 3 to position 1 with cost 0, and move position 2 to position 1 with cost 1, and then the total cost is 1. This example, cost 2 because I have to move 1 and 2 to one position. One at 1, the other is at this position. Then we can just go jump 2, 2, 2, 2, because every time we jump 2, the cost is 0. And eventually, either we'll jump 2 onto it, but in this case, because the difference between these two is an even number, no, odd number, so we jump, so we cannot jump to this position, right? Because a +2, +2, +2 is always going to be an odd number, so it will go either 1 before or 1 after, and then we have to do one more to get on. Okay, so I have 100, and we need to find the minimum cost. All right, minimum cost. Well, let's see, minimum cost. For all the chips on the even position, right? All the chips on the even position, they can go to one position easily. All the chips on the odd position, they can go to one position easily, and this will only cost 0, right? And then after we group those two, then we need to put them back together, and that will cost, so like this, because 1 and 3, everybody can go back to 1, right? And 2 need to go, so that one's 1. And this is already adjacent. So everything on odd, everything on even is already there, so we have to move the smaller amount. So that's what I think it is, right? So we have a bunch of things, because eventually we say we want to put everything into the same position. And that position can be either even or odd, right? If the position is even, then all the chips that are currently at even position, they have 0 cost to move there. If it's odd, then all the position in the odd have 0 cost to it. But eventually, the even one needs to move to the odd, which will cost 1, right? So therefore, all we need to do is, and every even one can move to 2. Every odd one can move to 1, right? So at the end, it's just to compute the total number of chips on the even position and total number of chips on the odd position, and return the smaller of the two. So that's my solution. I just realized it'll be bad today because this question is old, and I'm going to deal with the wiggle sort, which is also an old question. We did it yesterday. If we're only going to do 2 questions today, then we are not making progress. Now, the whole point is trying to make progress every day to hit that 1,000 mark. Well, yeah, it's like 600 something, so it's not enough. It's not enough. All right, so basically what we need to do is, what can I say, count even. So count even and count odd, right? Both are 0. And we'll say for P in positions. Can we do better? Let me see. I mean, we can go everyone and 1, right? That gives us even and odd. And we have zeros, right? And we have zeros, and we have ones, okay? Now we have zeros and ones. Ones are the odd numbers. Then we just sum them together, right? That's the total number of this, and then return. Yeah, maybe this one will be a better one. Hold on, let me see. So we can say sum, right, for P in position. We say P and 1, right? So we sum this, and then we say this is total odd, right? Total odd is this. Now when you return total odd if, say, len position minus the total odd is larger than total odd, else n equals len position. Right, we return total odd if the total even is larger than that, else we return n minus. I can just do this. Let's not do this. I just say total odd and total even equals this minus total odd, and then we say now we can just return the minimum of the two. Right, return the minimum of total odd and total even. Okay. All right, we'll go some test case. I have 3, which I think is right. 1, 2, 3. This one return 1, right? 2, 2, 2, 2, and 3, 3. This one return 2, and 1. Whatever this one is, will return 1. And here is position, and this is min cost move chip position. Yep. Have any edge cases? 1. All right, how about 1? Interesting. Then this one shall have 0 steps. Oh, well, we can do that. 0 steps. All right. Let's go for it. Yep. And also check this one. This one is they recycle hard all these problems. 1217, all even position the chips can move to position 2 with no cost. All odd positioned chips can move to position 1 with no cost. Thus, the minimum cost is the minimum count of chips in position 2 and 1. And 28. 90. Okay, and it goes through this minimum, even, and odd count. Okay, so look at this. Okay, it is the first attempt. Yeah, this basically the first attempt you're trying. It determines a lot. It says a lot. All right, this is the initial. Why this one's 63%? Anyway, we did do it a little bit differently. All right, that's fine. All right, now I'm gonna go with the wiggle sort. So I'm gonna pull up the wiggle sort again. Let's see if I can really reason myself out of this. All right, the condemned wiggle sort. All right, let's see if I can make a good explanation out of it. And we're definitely gonna do two solutions, right? I'm gonna do two solutions. So this is solution 1. But I'm gonna go through solution 1 first, and then we're gonna handle solution 2, and we have another one, solution 3. Okay, so wiggle sort, right? The very first observation is that for a wiggle sort, a sorted wiggle sort thing. So let's just take a look at this. So this one is sorted. Let's pick a better example. Let's take this one. You know what? No, let's take this one as an example, so we can kind of walk through. So this one has been sorted, and now we're gonna split it into two parts. So we're gonna split into the even position part and odd position part. So how do we do that? So we do that like this. So we use the dot to represent the missing value, right? And then now we're going to do the even position part, would be 3, right? So this is dot 3 dot 3 and dot 2, right? So we have the even position and odd position. And from this, what we see is the even positioned values are all smaller than the odd position value. So that is a hypothesis, right? So the hypothesis, well, maybe if we get all the even position small and all the odd position large, then we can just intertwine them. Now this is what I had the idea. I had the same idea yesterday, but then we run into the issue, the infamous issue of 4, 5, 5, 6, right? Because if I say, okay, I have the smaller is 4, 5, so I say, okay, I'm going to do 4, 5, and the large is 5, 6, right? So we do 5 and 6, right? Then we realize, oops, it's not going to work because of 5 and 5. Right? They have duplicates, right? So, but we're going to save this for later. So right now we need to prove, right? We need to prove that all wiggly sorted list can be turned into the shape where the even position values are smaller than the odd position values. Now there's a good proof for it. So how do we prove that? Let's say we don't have this, right? Let's say we have a value on it's wiggly sorted, right? It's wiggly sorted, but the value on here is bigger than the value on here, right? So can we make an example out of this? So the value on the even position is larger than the value on the odd position. So let's say we have a 2 here, okay, and we have a 0 here. Well, I think we can use 0. I can use 0, and we have a 1 here. All right. So this is still wiggly sorted: small, large, small, large, small, and large. Right? But we have a position here in the even position, which is larger than an odd position. Right? So if we have this situation, now this is the trick part, is we can always, if we have a pair of numbers of the even position and odd position where the even position is larger than the odd position, we can always swap them and maintain the wiggly sort, right? Why is that the case? Because this position, the even position, must be smaller than this and this, right? This is the only requirement for the wiggly sorted array. Is this even position is smaller than the odd position value to the left and to the right. Now, this odd position value is smaller than the even position value. So if we swap these two, then what we swapped into this position is an even smaller value. So if the original value satisfies the wiggly sort requirement, then the swapped in value also satisfies. So we can definitely swap 1 to this position. Now similarly, for wiggly sort on this position to work, it must be larger than the even position value to the left and to the right. Now what we swapped in is a value bigger than what's already there. So if the original one satisfies the wiggly sort requirement, then we swap in a bigger one will also satisfy. Therefore, given a wiggly sorted array, we can always perform finite numbers of swaps. Right? We can perform finite number of swaps such that we can end up with the evenly positioned values are always no larger than the oddly positioned values. So that is the basis. That is the basis for solution number 1. So we'll go back to solution number 1. So solution number 1 is we're going to sort the numbers, right? Sort the numbers, because we know we need to split the numbers into a smaller half and a bigger half. So we sort the numbers, we pick the middle of the number, and everything from start to the middle, which is the smaller part, we're going to put that into the even position, and we put the remaining on the odd position. All right, so seems fine. And that's actually what I had last time, but then I'm going to go into this thing. Now we have this issue. This we follow exactly, right? We have 4, 5, 5, 6. We break it into 2 halves. 4, 5 is the smaller half. 5, 6 is the larger half. But if we just do a regular, just like we don't make any change, we just intertwine these two, and then we have an issue because the 5, 5, they are right next to each other. We cannot do that. So why is that? Why that is the case is because these values, the 5 and 5, they are the median values. They're the median values of this entire array. And if we have duplicates of the median values, that makes things complicated. Apparently for 4, 5, 5, 6, we cannot do this, right? Because the 5 will end here and we start here, so they are too close to each other, right? So what else can we do? Well, what we can also do, let's say, we can also try to, so the whole point is try to get the median values as far apart as possible. So what is the strategy to make them far apart? It is to keep the median values on the even position as much to the left as possible, and to get the median value on the odd position as much to the right as possible, right? So basically we say we're going to go medium at the start, right? Let's just say a bunch of medium at the start, and then we're going to have something small values, right? Have small values going on, and then on the second half, we're going to put the larger value here, right? So we have the larger values here, right? A larger values here, and then we're going to have medium values, right? Medium values, like that, right? So this one works because the medium values on the smaller side is all pushed to the left, and the medium values on the larger side is all pushed to the right. So based on this, it works, right? And there's also proof for this, why this arrangement will always work, but I'm not going to go into that. It's in the discussion post, but intuitively it makes sense, right? And especially this question says at least one solution will be found. That means we won't have too many medium values. If you think about it, if we have too many in this case, right? How many we have? 1, 2, 3, 4, 5. It's a 10 number array, and we have 5 medium values. That's the most we can have. If we have 6 medium values, no matter where we put it, we can put it here. Then boom, we have a problem here, right? And if we put it here, then boom, we have another problem. So because it's guaranteed that a solution will be found. So if we have even number of elements, then the median will definitely be arranged this way. Now, if we have an odd number of values, then it is possible to have something like this, right? We're going to have something, you can actually copy and paste this. All right, and then on this side is a bunch of large values. Large values, large values, and large values. Right, so this is an odd number. So we have what, 1, 2, 3, 4, 5, 6, and 5. So 11. We have 11 elements, and this is the maximum possible medium values there, which is 6 medium values. Therefore, for even or odd, now the goal is just to separate the medium values. And once we separate, we can see that on the even side, we just need to put the medium at the front. On the large side, we put the medium at the end. So if we sort the original array, we just need to sort it in reverse order, right? We sort it in reverse order, and we take the first half, put that in the odd position value, and the second half put at the even position value, then we're done. So that's what solution 1 is, right? We sort it reverse, and we have, this is the first half from 0 to k, and our first half is the larger part, so we need to put on the odd position. So j is 1, and then we put on the nums 1, and nums 3, nums 5, yada yada yada, and then the second half we put on the 0, which is the even position. So that's that, right? A simple solution, but because we do sort, so we have O(n) log n time, and since we also copied the numbers, but we have to copy because we have to rearrange the values, so we have O(n) space. That's not what is required. Now, how can we improve this? How can we improve this to reduce, right? To reduce the time complexity and the space complexity. Now we can do time complexity first. Two observations, right? Two observations. First, what is the key is just the medium values. If we can arrange the medium values well, then the remaining small and the remaining large, we don't really care how they are ordered because it doesn't matter, right? We can be ordered, we can be not ordered, it will always work. Therefore, sorting is not necessary. So the only thing we need to do is to find the median value. Now, to find the median value, there is a question. Actually, it's inside here. I think it's a similar question. We can see kth largest element in an array. So this kth largest element in an array can be found on average in O(n) time. So if you sort, it's going to be O(n) log n to find the kth, but it would be easy to sort it and go to the kth. But if we don't want to sort and we want to do a O(n), there is a way to do this in O(n). So let's write that right now. So we need to find the median value, which means we need to find the k, right? the kth value in the entire array. So, but before we do this, we're just gonna to def, we should say kth, right, smallest value, and we're gonna pass in the nums, right, and then we're gonna pass the k. And what do we return? Well, what we need to return is the value itself, the kth smallest value. So how do we do this? Well, I read the solution, so I know we need to pick. So this is quicksort, right? Quicksort. In quicksort, how do we do? We do pick a pivot, right? And then we arrange the remaining values. Smaller than the pivot, put on the left. Larger than pivot, put on the right. And then we put the pivot back in. Then the pivot is sorted. And then we go left, and then we go right, and then recursion down to sort the entire thing. So we do the same thing here. We just need to pick a pivot. Right? We don't know what pivot it is. We just pick a pivot and then rearrange, swapping the remaining values in the array such that the value is smaller than the pivot on the left, value is larger than the pivot on the right. And then we basically say we have sorted the pivot, right? And then we put the pivot into its position. Then we check, right? We check if the pivot is on the left, if the pivot is on the left half or on the right half. If the pivot turns out to be on the left half of the array, that means the median value must be on the right side. So we do the exact same thing again on the right. Now, if the pivot is on the right side, then we recursion to do on the left side. Now, if the pivot is at the middle, then we return that value directly. So that's basically how this kth smallest value can do. So we have left and right, 0, and then len nums -1, right? And we do while left is smaller than right, right? While left is smaller than right, actually, yeah, while left is smaller than right, we are going to find the pivot, right? So we're going to say pivot is equal to nums, so we just randomly pick a value. So I need to say from random import randint, right? So when nums randint left and right, so we pick a value to be the pivot, and then we're gonna go from, we say after do that, we're gonna put the pivot to the front. So we say nums pivot nums L, so we put on the left equals nums L and nums. Let's call it P, easier to write. Right, so this one will put the pivot, the value at this pivot position. We'll put this value to the front, and everybody gonna compare to that. So now we're gonna do now we're gonna have 2 pointers, right? We're gonna have 2 pointers, say I and J, right? So I and J. So I gonna start with this, and J gonna start with len nums -1, right? And then we're gonna go through the entire thing and then do the swap. Right? How to swap? We say for I in range. Actually, I can just, I don't need to specify I. J is here. So I in range L plus 1. Oh, hold on. No. While I is smaller than J, right? While I is smaller than J, then we can say if nums I is smaller than nums L, right? If the I is smaller, then we just simply move I forward because this position is right. So we say I plus equal 1. L if, what if they are the same? The same is fine. The same is fine. So I think we should do this, right? If it's smaller equal to, then I just keep going, because if the value is the pivot, we can just keep going. That's fine, because the left side is going to be a lot smaller. Okay, so that's that. I'm going to say else, right? Else is the number I is larger. If it's larger, then we need to swap with j, right? So we just say nums I and nums j equals nums j nums I. So this basically say the nums I is larger than the pivot. We put the nums I back to the j, and after that, j minus equal 1. But we don't change I because we go back again. We're going to check again. So blah 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 blah. Eventually, what's going to happen is I and j will meet each other, right? I and j will meet each other. So they will swap, and I and j will meet each other. So they're going to come out. Then the I shall be the position. Let's see if I is the position where it's going to be. Let me think. So if I is smaller or equal to I plus equal 1, boom, we go to the larger territory and come out. That should be I minus 1. What if in this case, I is larger than, right? I say I is larger than j, and then I swap with j, and then j minus equal to 1, right? If it's larger, if it's smaller, I feel like it should be I smaller equal to j. Hold on, is I smaller to j or I smaller equal to j? If nums I is larger than nums L, so this one is large, then I need to swap with this, okay? So I swap with a j, right? And then j minus equal to 1, right? If it's a small value, getting swapped, right? If it's a small value, getting swapped. Then if we say j minus equal 1, I and j meet each other, then that is actually not right. Because this is so I and j swap, right? If position I is a big value, position I is a big value. If position j is also a big value, we can swap, and I need to minus 1, right? Hold on. Let me think again. The end situation. Okay, if nums I is smaller, okay, so now it's smaller. If it's smaller, then we're gonna swap. Now we don't swap. If it's smaller, we just keep moving I. So the current value is smaller, so we keep moving I to the next one and we check the next one. If it's larger, then we swap with j, right? We swap with j, and then we go back up. We check again. We swap with j until this value is smaller. Then we move forward, right? Now we move forward. Now if we move forward and they become equal, then I need to minus 1. If we move forward, yeah, if I move forward, because in this one I just keep checking, right? We keep checking, because every time I swap, j will go forward as well. So both j and I are going, right? Both j and I are going. So if I swap, j goes forward. Now they're equal, right? And they are equal. So in this case, I think when we get out, we need to check, right? We need to check. So when we get out, we need to check if nums I is if num's I, right? Because when we get out, it could be j minus 1 to get out, or I plus 1 to get out. So we're going to check. I'm going to say if when we get out, num's I is larger than num's L, then I minus equal 1. Otherwise, I stay the same. Now, we're going to do the last swap. We're going to say num's I and num's L equals num's L, num's I. So this one put the pivot into the right position, which is at the ith position. Now we do that. After we get that, now we're going to compare. We're going to see if it's so we see if the case, right? So we say it's the 0th, 1st, 2th, all the way to the kth position. And how do we check if it's the kth position? Then we say if I is the I as the index, right? As the index. Okay, so I is the index. And then we say if this index is equal to k, right? It's equal to k, then we're done. We just return num's I, right? If not, say if I is smaller than k, right? Which means I is smaller than k, then the kth will be on the right side, right? Then we just say L equals I plus 1, right? L equals I plus 1. Else, if I is larger than k, then we need to go the right equals I minus 1, right? Then we go back, and we go back, eventually, oh, I think in this case, because I probably need to go smaller equal to, because both are moving, right? Both are moving. R is moving, L is moving. Let's just say smaller equal to. And eventually this one will come out. Say if I equals k, it will definitely fine. So this one will definitely be met. So that's the kth smallest. Okay. We probably need to test this just in case it's if it's correct or not. How do we test this? We go here, right? And we just say print kth smallest value nums, right? So I'm gonna do this. I'm gonna run it. Missing one position. Oh, we forgot a k. So the kth. So this is 1, 2, 3, 4, 5, 6. That's 6 values. So it's the third, 0th, 1st, 2nd, and 3rd. So which one? Which one? I think we need to find the length divided by 2. If it's 7, length divided by 2 will be 3, right? 0, 1, 2, 3, and then we have another one here, right? That's 7. So the third one, yeah, the third one shall be, okay, so k shall be length nums divided by 2. Oh, we have index out of range. The first one give us 4, which is 4, 5, 6. That's correct. Second one give us 2, 1, 1, 2, 2, 3, 3. Correct. The third one we have issue. The third one we have index out of range. How? Random int L to Y. Huh. Random from L to I, it should be L to I. And L to I will, L is I plus 1. R is I minus 1. Hold on. And let's check this. Let's print. Right, print L and I. L and R and let's see. So we have 0 and 3. Okay, 0, 1, 2, 3. And then I probably should print out P as well. Let's kind of see. P is 5. Oh, what the hell? P is the position. My bad. Okay, so now we can get every value. So the first is 4, right? The first is 4. And the numbers are sorted. I didn't sort it. I just moved them around. So this is 4, and it's going to be 2, which is actually pointing to this position. Oh wait, 0, 1, 2, 3. Hold on, which position should we point to? No, it should be this position, right? And this value should be 1 instead of 4. And this one is 1, 0, 1, 2, 3. Should point to the number third one. Okay, so that should be plus 1, right? No. 0, 1, 2. That's 6. 6. I think it's this one. 7 shall be this one. But 6 shall be 0, 1, 2, 3. That's correct. But this one should be 0, 1, 2, right? It should be 2. Shouldn't be like this one minus 1, right? Minus 1. Oops. Oopsie daisy. What the heck? I cannot do minus 1? The case, right? So we're talking about the case is position. So this one, the position shall be this, the third, 0, 1, 2, right? So if this is 6 minus 1 is 5, 5 minus 2. So k we want is 2. And why we have this issue? Okay, let's do L, R, and P. Just kind of take a look. What happened? We have 2, 2, 2. For 2, 2, 2, nothing happens here. And IJ I and J. What is J? J is, oh, this is not right. J shall be R. J is R. J is R, right? J is R. And this one will break. And this one, nope, still have the same issue. Anyway, so it's a 2, 2, 2. So this one will break, don't do anything. Nums 2 and smaller equal to the left. That's true. No, hold on, we're not doing this one. We're going to say nums 2 larger than nothing, so I is, and I equals to k. I equals to 2, right? K is 2. How? How is this one not right? Wait, hold on. This one's right. Alright, the problem is not with this one. Maybe the problem is with this one. Yep. So, problem is with this one. How? Why would I have problem? So start from 0, 5, and a 1. 1 will be 3. And then that's too big, so 0, 4. 4. Okay, we probably need to print out the print out the nums as well. this time it works, but sometimes it doesn't work. Okay. Right? And then 0, 1, 2. And I'll pick 1. And then 0, 1, 2. 2, 2, and 2. 2, 2, and 2. So nothing changes. This one doesn't go. And this one doesn't go. This one is the same. With the left, we'll swap with the left. Yeah. And I shall equal to k. I is equal to k. K is 2. And I is 2 as well. Hold on. I is not 2. I is not 2. Oh, I is not 2 because I do not. Hold on. So when it comes out, if I is larger than. Because I set it to L plus 1. And then blah blah blah, when we've done everything, you say I need to minus equal to 1. Oh, it's easy to do. We just say if come out I is larger than, well, if I is yeah, that handles situations if it's equal, right? If they break out because I and j are equal. Well, in that case, what if we do equal? I and j are equal, so this one is smaller to this, right? So I is smaller or equal to L, then I plus equal to 1. Now we go to j territory, go back, and then I and j is the same, j minus 1. So we can actually just do, if I say this is smaller or equal to, then I just need to do this. There we go, right? And then we got 2. Okay, so I think we fixed this now. Let's go through everything and check. Everything works. All right, first one is 1. Second one is 2. Third one is 5. The last one is 1. So now we get the kth smallest. Okay. So this will be our, what do we say, m, right? M, our medium, right? We'll get the medium. Now, once we get the medium, we can actually use the same technique as this to move all the medium values to the middle. And all the values smaller than medium go to the left, but without sorted, and all the values larger than medium go to the right without sorted. So we use the exact same, but not exactly the same, almost the same. So we're going to have an I, J, and a K. All right, so I am going to go to the left. J is going to be on the right, so land nums minus 1. K, so what is K? K is the current position. So K is the current position. So J will point into the most right position that have not been. Let me put it another way. From j plus 1 to land nums minus 1, all those values are larger than medium. From 0 to I minus 1, all of them are smaller than m. From I to k minus 1 are all the values equal to m. Right? So with these in mind, now what we're going to do, we say while k is smaller or equal to j. Right? So we want k and j to meet each other. So we say if nums k is smaller than the m, right? Nums k, so the current value is smaller than m. Now what do we do? So we're going to swap with I. right? Because we want the smaller value to go there. So we say nums I, nums k equals nums k, nums I, right? When we swap, then from 0 to I is smaller or equal to actually we can put it here. 0 from nums 0 to nums I minus 1, all smaller than m, nums k plus 1 to nums len nums minus 1, the last value, all of them are larger than m, and nums I to nums k minus 1 are equal to m. So that's what we're trying to maintain. So if this is this, and then we swap, but now from 0 to I are smaller than m, therefore I need to plus equal 1, right? Aleph nums k is larger than m, right? So we have larger than, then we're going to swap. Num j, so move the j here, nums k equal to nums k and nums j. So we swap, and after swap, from k to the end, no, hold on, not k to the end. This is not k, this is j. From j to the end are larger than, so we need to, j need to minus equal 1. And else, now is nums k is equal to m. Now this is tricky. Nums k, right, is equal to m. Therefore, this one is violated. So we need a k into plus equal 1. So we keep going this. Eventually, k gonna meet j. So when k meet j, what do we do? When k meet j, if it's smaller, right? When k meet j, if it's smaller, then we're gonna swap. And I plus equal 1. I plus equal 1 is not enough because after we swap, we basically swap m. Oh, that's fine. So this one, because from I to this always equal to m, so once we swap this, I plus equal to 1. No, hold on. If we swap and I plus equal to 1, then I will catch up to k if my k do not change. So actually k needs to plus equal to 1 as well. K needs to move forward as well. So because this is at the beginning, right? If we have not encountered any m at the beginning, I and k must go together, right? They go step by step together until we meet the first m, and then k will go forward by itself. And then if it is still smaller, then we're gonna swap, right? And then after swap, we move forward. So I and k will maintain the same distance. And if I have more m, then their distance will be larger. So eventually, k will encounter j, right? When k encounters j, if this value is smaller than m, then we're gonna swap with I, which is m, and then both so I will still point to m, but k will move forward, right? K will move forward into the territory of j, which is too big. Now we break out.
What?
If this is the case, if it's larger than num k is larger than, then we're gonna swap with j. Basically, it's nothing. Then j minus equal 1, and then we break out. And if it's same, so whatever the thing, once we're done, k needs to minus equal 1. This will put k back into the last median value. So k now is at, let's say k is now at the last median value. So once we find this, then what? Then we can simply move the values around, right? We're gonna move the values around. How do we move the values around? Well, we do need to create a new So actually when we do this, we need to copy. We need to copy the nums. When we say nums copy equals nums, right? We're going to copy it because this is like the semi-sorted, and when you put the semi-sorted back into the nums. So all of these has to be semi-sorted. So we're going to do this. So nums copy. And here, now we can do from start to k. Well, actually, what is it? K? K is pointing to the last median value, and I is pointing to the first median value. And K and I doesn't really matter because all matters is nums copy now is sorted. So we just need to get the median, this position, right? So this is the position that we need to handle. This is the position. So we grab this position, right? We grab this position and we go reverse order. Okay. So let's also do mid. We do need mid. So this is our mid, and this is gonna be mid. We don't need to use k anymore. We just go mid, from start to mid, and from mid to the end. Right. So we're gonna say for here's I in range. So we're gonna go from mid. That's point to the mid value. So from, hold on. Are these the smaller values? So smaller values going to the even position. So these are smaller values from start to mid. Mid actually +1 because we want to include mid. So for this, and hold on. We need to do reverse. So from mid all the way to 0, right? And then we have a J again. So let's call this rearrange, right? Create the wiggly sorted array inside nums, or inside nums. Okay, so J is going to start from 0 because they are put into the evenly positioned value. So we just say nums J, right, equal to nums copy I, right? So nums copy I, and then J plus equal to 2. And the next one come up, so we'll go mid, and then mid -1 all the way down to 0, right? So that's to the odd, even. Now we're gonna do odd again for I in range, but now we're gonna go for from len nums -1, right? Len nums -1. We'll go from len nums -1. That's the bigger value, all the way down to mid, but not including mid. And then we say nums J equal to nums copy I, J plus equal to 2. And once it's done, and we are done. So that's solution 2. Let's see if it works. It passes. So this one, okay, so this one is using, this one is O1, ON time, and ON space. Right? We use kth smallest value to find the median, and then rearrange a copy of nums such that all the median values are positioned correctly and all the values smaller than median are pushed to the left, and larger, and those larger than median pushed to the right. The smaller or larger values themselves, smaller or larger values themselves are not sorted. And finally, nums are populated again, just as in solution 1. And it has to be doing like in reverse order. Okay, so let's try this and see how this one goes. Oh, we forgot to also need this kth smallest helper function. Okay, so let's here. Try it. We shall pass, right? And then we submit this and see how long it takes. Doesn't really matter how long it takes. I just want this to be correct. Yep, it's correct. Gonna take a whoa, why it takes so long? 5,000 milliseconds. I do not did I do it wrong? Why it took so long? Now I'm not confident. Yeah, this is right. This is rearranging. And then we go to the right side, go to the left side. And then this one we swap. Swap. Yeah, I don't see. I think this is the same. But I'm surprised. Oh well, we do have the copy part, so the copy might be an issue. The copy might be an issue, but check. So I want to check the solution, see if it's the same. So which one? This one. This is a good post, very good post. I learned a lot from this one. I mean, Pachman is still the one that I think he came up with the actual idea to do 001 extra space. But anyway, so we do this already, right? Kth smallest sort. We have a get middle. They do a random thing here and then get middle, while this, let's see, well, I get middle here, and then smaller, hold on, what? This is different. Oh no, this is the other one. This is the other one. If it's smaller, then we swap. They have to go through the entire thing, and then when I come out, what do we get? We swap. We return I. And then we check. This basically corresponding to this. All right. Here on R. Come back. Maybe I did do one more round, because this is smaller. Should not miss. Maybe smaller to R is okay. Well, if left is equal to, then that should be fine. I like to do it this way. And then the actual sort itself, yeah, I think we follow it exactly. Yeah, right? We do have the copy, and then we do this part. If it's smaller, right, then we swap. Both have the plus plus. Now if it's larger, we swap one of them, and then we do this. And eventually, we run this copy. Yeah, so that's fine. I mean, the time complexity doesn't really, the time doesn't really matter that much. Okay, so now the last part. So the last part will have the same as this to begin with, right? To give us the medium. So we're gonna get the medium. But now the trick is in here we rearrange first and then put them into the position. Now the ideal is what if we can, right? If it's possible for us to rearrange and put in the position at the same time, right? So if you think about this, when we put the values into position, we just throw them to the left and throw them to the right. But what if when we throw them to the left, like air quote, throw to the left, when we do this, right? We not only throw them to the left, but also we throw them to the correct position. And if you think about it, here, right? These represent the left, and these represent the right. Now they are not exactly, like the left side of the array, but if we can assign, if these values, if these can be considered the left side, a quote-unquote left side, and these can be considered a quote-unquote right side, then when we throw to the left and throw to the right, we actually throw them into the right position, right? Therefore, when we say throw to the left, right? So let's say I is equal to 1, right? And then let's say k is equal to 3. And I want to throw the value, and then we have nums k is smaller than medium. So we want to throw this value at position 3 to position 1. Right? That's what I say, throw to the left. But what if when I throw to 1, we're actually not really going to 1, but we're going to this position. Right? You see what I'm saying? We're going to this position. Or when we throw, like, how should I make it? So basically we want a new mapping, right? We want a new mapping when we throw to the left and throw to the right. We want a new mapping. So what if we map the 0 in the original array? 0. No, not original, the 0, the imaginary, our imaginary index is 0, and this one is actually corresponding to 1. Right? So whenever we say we're gonna swap with 0, we actually swap to the position 1. And when we say 1, we swap to position 3. And 2, we swap to position 5, right? And 3, we swap to position 1, 7, and if it's 4, we swap to 1, 3, 5, 7, 9, right? So basically now what we're doing is we will get the big values. If anything is big, we will throw to the left. That's really different from earlier. We say if anything is big, we throw to the left, but then we actually we throw to the left, virtually left, but the mapping it actually goes to these positions. So these represent the left, which is the larger thing, right? And we keep going. Now the right, so the 5 will be mapped into this, to 0, right? 6 mapped to 2, 7 mapped to 4, and 8 mapped to 6, and 9 mapped to 8. And then if anything is smaller, we will throw them to the left, which is represented by these things. Okay? So once we obtain this mapping, right? Once we obtain this mapping, and then we can do the ordering and repositioning at the same time. Now, how do we do this mapping? Right? What is this mapping? Well, this mapping, I mean, I already know, but what we can do is, let's say if this is I, right? If this is I, and this is, we say, a map, let's say mi, right? Then m will equal to lambda, or passing I, right? And we say 2 times I plus 1. 2 times this plus 1. 2 times this plus 1, right? So we can handle 0 to 4. But how about 5? 2 times 5 plus 1 is 11, right? So we need to wrap around. So this whole thing, we need to wrap around some value. Well, you see here, we need to wrap around, let's say n plus 1. N is the length of the array, right? So it fits this. If it's 6, 2 times 6 is 12, so 13. Mod 11, that's 2. Okay, so that works. What if we have this case, right? We have this case. So in this case, we have a 10, right? If we think about it, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we have a 10 need to be mapped to what? 10 need to be mapped to 0, 2, 4, 6, 8, 10. 0 need to be mapped to 10. Does this work? Well, in this case, 2 times 10 is 20. 21 mod 21 mod 11 plus 1, that's 12. 21 mod 12. That's actually not working. How is the others one? All the others one working? Hold on, let's try it again. So this one is 1. So these will always work. So 0 to 4, right? Will always work. 5. 5 is 11, and this, oh, this is 11. That'd be 12. So we cannot. So therefore, if it's even value, we need to add 1. If it's odd value, we need to remain odd, right? We need to remain odd. So one way to remain odd is use this. Now, these all work, but how about this one? Original position is 10, right? And then we do 20. I mean, even these, 0, 2, is this one work? 2 times 9, 18, 19. 19 mod 11. 19 mod 11 is 8. Okay, so this is 21 mod 11. 21 mod 11, oh, it is 10. 21 mod 11 is 10. So that is our M, or what Pachman says, the virtual indexing, right? So if we go here, we're going to do a M is equal to this. Well, we need a, it's going to be len nums, right? And then we're going to do exactly the same, not exactly the same. So we do this, right? But we do not need to copy. And we're going to say I, J, K are virtual indices, right? What this means is we use IJK as the overall scheme, but underneath, when we say nums is not nums K, we're going to say mapping K to the new values. And everything need to do the same. So it'll be like this. So all these, because we don't need copies, right? And everything needs to be mapped to this function M. And once it's done, now we're done. A virtual indices. And then we're going to say virtually the following must hold. Okay, so we do 3. And we try it. Oops. Alright, this is not right. Okay. This is not right. Six, 1, 5, 1, 4. Oh, I know why. Because I need to. This is putting the larger value on the odd position. So no. So if it's larger than, we put in the odd. Put in the left half. The left half need to be bigger, and the right half need to be smaller. So it's like this. Reverse this, and we pass. Okay. So we're going to do the last one. So this is virtual indexing. Virtual indexing to make the complexity, to make the solution O1, O1 in time and O1 in space. This is from Mr. Hoffman's idea. Okay, so I'm going to just pass this last one and I'm going to call it a day. We still use the k smallest value. Yeah, this virtual indexing idea is really neat. Okay, try this. Now, without copy, I think it'll be faster. Huh. Not really. It seems like this kth smallest value is taking a toll. How about O(n) log n time and O(n) space? Right? So basically, we say we don't use the other solution. We say this is O(n) log n time and O(n) space. So we sort it first. So we got a mid and this one, and then we sort. So nums.sort. And m equals nums mid. And mid only appears once, so I can just do this. I'll run the code first. Okay, let's see. If this one is slow, fast, I mean the problem is, yeah, this one is fast. So the problem is with finding the case. I don't know. Is this I can actually go to my solution for finding a case. We've done this one as well. Oh, this is case largest. It's different from case smallest. But I've done it, so let's just double check if the two code are the same. If they're the same, then there's nothing I can do to make it faster. Yeah, it's the last piece. Right? We locate a pivot. So we locate a pivot. We have L and R, which we do I and J. Right? And then we swap it first. Now pivot is random. We swap it. J do this. For J in range. If it's smaller, now we rotate J plus equal 1. Wait, are we not moving I? Oh, I moves here. I always move forward. Oh, I always move forward every single time. Yeah, my I is... Hold on. If this is smaller than, we will swap. And then we'll swap with J. Oh, that's the case largest, that's why. So if the case smallest, are you saying J, I will be incrementing no matter what? If I is smaller than, if I is larger than, how can we keep incrementing? If num's smaller than this, now we swap the two, and J plus equal 1. If num is equal to, or larger than, now this, like after we swap, so I and J, I swap, and then I move forward. How? You say I is smaller than this, right? And J is there. I is smaller, so we will swap the two. What if the J swap here is also smaller? I don't know. But if you look at this, it does only go one side. Okay, J is this. J is smaller equal to right. And then if J is smaller, then we'll swap I and J. What we want to do is to keep the smallest, right? So if nums J is smaller than nums L, and I, hold on, I is at L. I is at L. Wait, in this case, I is also at L? Both is at L. Okay, I is at L, right? So we say if J is smaller, then we will swap And after swap, I is going to increment. Well, actually before swap, I increment, and then so I increment, and then we swap. So if this is on smaller, then we swap. So we guarantee that I is at this position is the smaller than. The one is smaller than L. So we put the smaller one to here, and whatever is at the front will come to me. And what we're saying is that value will also be smaller. That value will also be smaller. Why? Because at the start, if it's smaller, then I will swap with I, right? I will swap with I, and then we both move forward. If it's still smaller, I swap with Y, we both move forward. If it's larger, if the current value is larger than I, okay, if the current value is larger than the pivot, then I will move forward, but we leave I behind. So I will always point into the value which is larger or equal to, okay? Now go forward. If it's still larger, we'll go forward. If it's smaller, then we'll swap. Oh no, this one's larger, then we'll go for, oh, shoot, that is correct. Okay, so, I is equal to, okay, I is equal to L, right, and I will say for J in range, L plus 1 all the way to R, right? So I'm going to say the loop condition, right? The loop invariant is nums 0 to nums I minus 1, all smaller than nums L. Nums nums J, right, to the end. Now nums I to nums J minus 1, right, J minus 1 are because if it's smaller, then we swap. Right? If I am smaller than this, I'll move this one here, and then this one. So these will be larger or equal to nums L. That's the loop invariant. So if that's the case, then we say if nums I is smaller than nums J. Oh, hold on. Nums J is moving. Nums J is smaller than nums L, right? Then we're gonna swap. Now we're gonna swap I and J, right? We swap I and J. So for the smaller to the I, and because I will point to something larger, so after swap, nums J is good. So both J. So after this, I need to plus equal 1, because after swap, nums I will be pointed to something smaller than nums L. Oh, that's smaller than, right? If it's smaller than, then I need to plus 1. If it's equal or larger, then I simply move the J forward. Yes. And once we're done, I is the value pointed to. I is the first value. So we're going to swap I and L. And we say if I is equal to K, the case. Otherwise, okay, so I modified this. Let me try again. All right. J all the way to the end. And everyone is larger or equal to nums. So I pointed to the first one that will be equal to or larger than nums. Now we swap. How this one is kind of reversed. Now we swap nums. Yeah, we swaps I and L. And then we get this, right? And then we say if I is smaller than left is I plus 1 and right is I minus 1. I also return nums I. What did I go wrong? I equals L. If it's smaller, then we swap. Oh, I need to plus equal 1 first. True. I need to plus equal 1 first. Yes, I need to plus equal 1 first. Because when I swap, I want to swap J, which is from a smaller value, to the front. So to the front, I need to swap to, because all the way to I, current I is the unknown of value, right? Current I is the bigger value. So when we, wait, hold on, let me think again. So it's this. And we say 0 to I minus 1 is smaller, right? Then when we swap, if it's a small value, and I swap with I, and I is at 0, right? So I need a plus equal 1. If this J is smaller than nums I, then I plus 1. When we do this, and after that, J goes forward. And I find another one if it's smaller, then I plus 1, and push 1 goes here, and then this one goes to J. So I is keep building up the smaller. Every time a smaller one, it goes here. Every time I have a smaller one, it goes to I. So if we start with a bigger one, then we just keep moving. So basically, this is not right. So everything from left to I is smaller or equal to, and from I plus 1 to J minus 1 is going to be larger than. So every time we find a value, if it's larger, then we just keep moving, doesn't matter. If we find someone that's smaller,